Good morning, good afternoon, good evening, wherever you are located in the world today, and welcome along to the AMETEK Solidstate Controls webinar for this month. And this month we are revisiting a webinar that we did the first time back in April of last year. And we're going to discuss how do rectifiers work, basically how do charges rectifiers work. So the first thing I'd like to ask, as always, is can you hear me? If you could type in the chat on the right hand side that you could hear me, that would be really appreciated, because I don't want to speak and not be heard. While I wait for somebody to let me know, I'll introduce myself while everybody is logging in. Thank you very much for letting me know. My name is Craig Williams. I'm the Senior Technical Manager for AMETEK Solidstate Controls. I work out of the Stafford office in Houston, Texas. Can't you tell by my accent? I have 20 years in the industrial UPS industry. Actually, it's going on 22 years now. And I've worked with all the major UPS charger manufacturers. I've been with, this is my 6th year with AMETEK Solidstate Controls. There will be a lag of around 30 seconds between you hearing my voice and me seeing any reply to a question that I ask. Basically, the platform we use is Webinar Jam, and they have to take this webinar and then broadcast it over iOS, Android, and Windows-based systems. So there is some processing time that takes place. So when I speak, it's going to be about 15 to 20 seconds maybe before you actually hear me. So therefore, when I say something and you type in a question, I'm not going to see that question until about 15 to 20 seconds after I've actually said it. Hopefully that makes sense. So therefore, what I tend to try and do is I'll save the questions until the end. And it is much preferable that you put them in the Q&A rather than in the chat, but I will look at both to make sure I catch them. Webinar Jam has a panic button. What that means is if the webinar crashes, then I can press the panic button and everybody will be kicked out of this room, and we will reconvene in another room that webinar automatically creates, and we take over from where we left off. A very popular question is, will the webinar be recorded? And yes, the webinar will be recorded. Webinar Jam records it itself, and if you are registered for this webinar, you will receive a link after the webinar is complete for you to go in and rewatch it at your leisure. But the problem with the Webinar Jam version is that once you press play, there's no fast forward, rewind button. You can pause it, but you can't fast forward and rewind. So it gets played as if it's a brand new webinar. So what our fantastic marketing team do is they go in, they convert that to an MP4, and then they upload it to our YouTube site. And in doing so, it takes about a day for us to do that. You will receive that link tomorrow if you've registered, and you can go to our YouTube site and you can watch it, pause it, rewind it, share it, do whatever you want with it. And the webinar should last around an hour, but as always, that depends on how much I waffle on, and I do tend to waffle on sometimes. I do apologize. I just like talking about this stuff. Okay, so let's get started. Today we're going to cover the following objectives. Understand what a charger rectifier is. Then we're going to understand the major components of an SCR-based charger, and I'll explain what SCR-based chargers are. Discuss how controlled rectification is achieved, where the term rectifier comes from. Discuss SCRs and diodes and how they work. Hopefully I can explain that for you. And then we'll discuss feedback control and how the system regulates its output voltage. So that's the main objectives today. So what is a rectifier? Well, a rectifier is is also called a charger. The two terms are interchangeable. Rectification is basically changing AC into DC, and that's what a charger does as well. So if somebody calls something a rectifier, it's really still a charger. The reason that most people call a charger is because there is a battery connected to it, okay? And the explanation that we've got there is the device that converts alternating current AC, which periodically reverses in direction, in North America it's 60 times a second, to direct current, which flows in only one direction. And there are two main types of rectification. There's a half-wave rectifier and a full-wave rectifier, and we'll discuss both of those today. Rectification is used in chargers to convert AC to DC to charge batteries and to also supply DC loads. And those loads can be switchgear systems, emergency shutdown systems, firing gas, telecoms, PA systems, and numerous other things, DC lube oil pumps, lots and lots of other things. And obviously, it can also be the component of any AC UPS system. If you have a full AC UPS system, the AC's got to be converted to DC, and then that DC gets converted back to AC. So hopefully everybody's following along. Okay. So the components of a charger system. We're going to talk about the transformer, the Thyristor SCR diode bridge, and we'll go into the term Thyristor and SCR, but basically they're interchangeable. An SCR is a Thyristor is an SCR. Just in Europe and in many other countries, they call an SCR a Thyristor, and it's similar to Kleenex. You know, when you go for a tissue, most people say, I need a Kleenex. Well, an SCR is a silicon controlled rectifier, but the first company that came out gave it their own labeled name, which was a Thyristor, and that caught on. So when people say a Thyristor, it's actually the first major brand of Thyristor SCRs that came out. Okay. We're going to talk about the filter circuits, the choking capacitors, and we're going to talk about the control circuits today. I don't have time to go over absolutely everything that's in a charger. Okay, so here is the basic single line diagram, block diagram of a charger. So on the left-hand side, you have your AC input coming in, and for an industrial rectifier similar to what AMETEK SCI makes, that's usually going to be 480 volts, three-phase. Okay, we have started making a single-phase charger, but there's not many out in the live yet, so it's 480 volt three-phase that we usually deal with. That then goes in through an AC input breaker into a transformer, and for our system that will take that 480 volts, and depending on what the output is connected to, if it was 120 volts DC nominal, then that's going to step down on the other side of this transformer to about 130 volts. But we'll explain that as we go on. And you can see that's AC going into that side of the rectifier, and then we have DC coming out this side. That is the simple basics of a single line diagram. Okay, so the transformer. Let's talk about that first transformer. The main purpose of the input transformer is to step the grid AC voltage, or the voltage coming from the utility company, down to a level suitable for the DC output. And for an example of this, a nominal 120 volt charger with a three-phase 480 input will need the transformer to step down from 480 volts to approximately 130 volts to allow adjustment. And I'll talk about that in a moment. You know, this is basically how to work out the average volts DC. It's a well-known engineering calculation. But this is what we're looking at here. The volts DC is equal to 1.17 times the volts RMS. Okay, so let me go back. So therefore, if we have a nominal output of 120 volts, then 1.17 times VRMS, if we say that the secondary is 130 volts and we times that by 1.17, I'm going to do the quick math on my phone because I'm not intelligent enough to be able to do it in my head. It is 152. Now, obviously, 152 volts is too much for a 120 volt system. And we're going to discuss how we can regulate that voltage later. But what we can do is we can say that's the maximum voltage that this charger will be able to put out. But if we add some regulation circuits in, we can actually work between 152 down to a certain voltage, depending on the regulation. So keep that in mind. So that is why we need a step-down transformer on the input to our rectifiers. And also the other thing that our transformer does, because it's an isolation transformer, it acts as galvanic isolation. And it's the principle of isolating functional sections of an electrical system to prevent current flow. And what it's saying is there is no direct current between the primary wires and the secondary wires. There's no, I didn't mean direct current, there's no direct connection, okay? They are just wound round the core, and the magnetic flux in the core induces a current on the output winding when you have a fluctuating current on the input winding. There is actually no electrical connection between those two wires whatsoever. So we can say that they are isolated from each other, okay? And that gives us many, many advantages. The DC in the charger can't reflect back onto the AC MCC that feeds the charger because it has that isolation. And there's many, many other things that a galvanic isolation transformer gives us. So the next thing we're going to discuss is rectifier diodes. So these are positioned after the transformer usually. And diodes are semiconductor devices with a PN junction. Now, I'm not going to go into holes and doping of semiconductor material. Sometimes we just have to hit the I believe button. So diodes are semiconductors basically with a PN junction. And they only allow current to flow in one direction, which is anode to cathode. Okay. Now, a lot of people ask me what is a mechanical equivalent of a diode, and you can see it on the screen there. The mechanical equivalent of a diode is basically a check valve. Okay. So we have positive on this side here, and we have negative on this side here. So that means we have flow in this circumstance of oil flowing from right, this side here, to left. And that pushes the valve clapper back towards the left and allows the flow of oil to flow that way there. So we are saying that when the positive to negative is in the correct configuration, then oil will flow in this pipe. Actually, let me go back. So if I was going to draw the diode, it would be drawn like that. Excuse my terrible drawing. So we have to have positive on the anode with respect to the cathode to allow current to flow in that direction in the diode. Okay. And here are some good examples of rectifier diodes. So this is the electrical symbol for a diode, as I just drew on the previous page. And here are many different types that you can get. This is a stud-mounted diode. And the configuration, usually on every diode, there is a little symbol drawn. So on this one here, it would actually be drawn like that. That tells you which side is the cathode and which side is the anode. So on this one here, this was the anode and this was the cathode. This is what we call a hockey puck diode or device. And basically the base, this whole base is conductive, and that is the cathode. And there is some metal that you can't see, a conductive area on the top of the diode, and that is the anode. And this type of diode has to be compressed between two heat sinks for it to work correctly. Okay, and you can see there is a symbol. It's actually right here, but it's drawn like that. That's why we know that the top part is the cathode and the bottom part is the anode. Here's another version. This is not actually stud mounted because the stud doesn't go into the heat sinks. What you have to do for this one is you get a purpose-built clamp that goes into the heat sink. So you don't need two heat sinks for this one here. You can just clamp this diode onto the heat sink here, and then you connect your wire onto here, and then for this one here, that would be the anode. And then the heat sink would become the cathode, and you would connect a cable off of the heat sink for the cathode. And the last device is this one here. This is a multi-pack, and you can see anyway, you can't see it very well, but there are two diodes in this pack. And basically they are assembled. This is the anode of one and the cathode of the other. This is the anode of one and this is the cathode of the other. And they can be connected in two different ways. And we'll go into that later as well. So here is the example of a half-wave rectifier. Okay, so on the left-hand side, we have the AC coming in. You can see it's AC because some of it is above the 0 volt line and some of it is below the 0 volt line. And it's important to remember that AC means the current will be flowing like that for the positive portion of this sine wave. Yes, it will only start off a little bit, but then it will push it harder and harder and harder, and then we're still going in the same direction. It'll get less and less and less. But then once we get to that 0 volt line, it then reverses direction. It alternates its current. So for this portion here, the current will go that way, and then it goes back to going that way. So that is why we call it AC. Now remember, we have our diode here. So we have our anode and we have our cathode. And the diode will only conduct when the anode is more positive than the cathode. Okay, and that only happens for the positive portion of the sine wave here. This is going to be more positive than this, which allows current to flow through to our load resistor in this circumstance. Okay, and that will allow this portion of the sine wave through to the load resistor here. Now, when we get to this portion of the sine wave, this is going to be more positive than this. So current tries to go around this way. And then when it gets to the cathode says, no, I'm blocking you. You are not allowed to flow this way. This is the way I am designed. And therefore, this part of the sine wave does not get through to the output circuit whatsoever. So this, if you put an oscilloscope across this point here and this point here and monitored the output of this half-wave rectifier, that would be the exact oscilloscope reading that you would see, the waveform that you would see. And the question is this DC? And it's a very, very good question. Is it DC? And the answer is yes, it is. Because even though we are still changing the amplitude of the voltage, the current is flowing in that direction for every pulse. So we actually call this pulsating DC. But it is DC because the current is direct. It is only flowing in one direction. Okay. So that is the most basic half-wave rectifier that you can get. Now, for a full-wave rectifier, you have to get a little bit clever, I suppose, on how to change the AC into DC. And what we're doing is we're flipping up both sides of the waveform and getting a full wave rectification waveform out. Let me just see. So we're going to start here. Let's say, so for this portion of the waveform here, this is going to be positive with respect to the bottom. So if we go here, we get to this junction point here. Obviously, we can't go down that way here because we have this cathode stopping us. So we can't go down that way. So yeah, let me clear that. So when we have positive with respect to negative, the only way that we can go is through the anode to the cathode of this point here, and then out. We've got a cathode blocking us there. So we have positive there with respect to the bottom of here where it goes back. Now, this part here confuses a lot of people because we have two anodes to choose from. So a lot of people say, well, we can go up that way if we wanted to. But then all we would be doing is getting to the same potential as we started with. So there's no potential across that diode. So current will not flow that way. The only way current is going to flow is through this diode here back to the negative. And that will give us our positive part of the sine wave on the output there. And then what happens is, for the negative portion of the sine wave, and this is where it gets very, very clever, this is going to be more positive than this. So if we follow the current along, once again, we can't go down that way. We go up here, and we go onto the same bus bar with our positive waveform, and then we get back to the negative through this diode here, back here. And what that does is it takes this portion of the sine wave and it actually flips it up here. Okay. And that is how we get full wave rectification. Many people call this an H bridge or a rectifier bridge because it looks similar to an H if you look at it like that. I like to use an H bridge in an inverter bridge. It's a better analogy, but some people do. And then this bottom one here, that is the exact same circuit, and that's probably how you got taught at university or tech school. But this bridge here is exactly the same as this bridge here. It's just drawn a little differently. That is all. You know, if we had positive, negative here, we would go down, out through there, back up, down through that diode there and out there. And then if we had positive there with respect to negative there, we would go down, up through that way, back up through that diode and back there. Cool. So that pretty much shows you exactly what I just drew with my pen for the positive half cycle. And then this shows you the negative half cycle. And that is what you will see on the output for a full wave rectified circuit when we use diodes. Okay. And this one here is a 3-phase diode bridge. And you can see, actually, if you just take these 4 diodes here, that is a single wave bridge. You've just got 2 inputs. All we've done is add another 2 diodes here and had a 3rd input here, and that's what makes it 3-phase. But it still operates exactly the same. If the positive cycle was between A phase and B phase, it would go up, out, through, down here, and we have to get back to B phase, so it would go that way there. And if it was B to C, then we would go along here, up here, down, out, and we have to get back to C phase, so it's that way there. And then if it was C to A, we would go along here, up, we have to get back to A phase, which is all the way along here, back there. So the diodes are always acting in pairs. Hopefully that's clear. And the output waveform for a full wave rectified bridge, basically try and think of this 0-volt line as a fold in a piece of paper. And then all we are doing is folding that piece of paper. And it's like when you used to make a butterfly at school with paint, and you painted one side of the butterfly and then you folded the paper over and it printed the other side of the butterfly onto the other side. That's exactly what we're doing here. But instead, what we're doing is we're flipping that up, and then we're flipping that up, which is the blue one, and then the black one, like that. So we are just adding all of those 6 peaks, the positive peaks and the negative peaks together. And you can see the resulting waveform is the green waveform you can see on the bottom here. Okay, so this is actually, if you measured it with an oscilloscope, excuse my terrible drawing again, that would be what you would see the waveform on your oscilloscope. Okay. And that's much more like what most people would consider to be DC. So remember we discussed the transformer and that it steps down the voltage, and that there was a calculation for what the secondary of the transformer is. And this equation here will tell you basically 1.17 times the VRMS of the secondary will give you what the output voltage DC is. But you've got to remember, this is very important. Everything is specified in North America for a 480 volt 3-phase supply. We don't know what your utility company is going to supply you. It could be 520, or it could be 460. We have no control over that whatsoever, and that's very important. So as I mentioned on the earlier slide, if we have 130 volts on the secondary when we have 480 volts on the primary, then the output voltage, which is positive to negative at this point here, will be 152.1 volts. Okay? But let's say we go down 10% and the input voltage is 432 volts. Our charger will still work. It's right at the limits of what our tolerances are. It's plus or minus 10% on the 480. But so 432 volts, it will work. But if we just had diodes, look what happens on the secondary of this transformer using the direct ratios, 480 to 130. So 432 would give us 117 on that transformer. And then if we did the calculation, That means the output voltage here now goes down to 136.9. So if there is a fluctuation on the input and we only use diodes on our bridge, there's going to be a fluctuation on the output DC, which isn't good. If you had batteries connected here, then that would possibly undercharge your batteries because the voltage has gone down. And similarly, if we go up 10% to 528 volts, our secondary will go up proportionally to 143 volts, and our DC on the output will now go up to 167 volts, which could overcharge your batteries. And if they were valve regulated batteries, they could go into thermal runaway. So we cannot use diodes in our bridge because it gives us no control for those swings in the input voltage to stop the output voltage going up and down basically in sync with it. So we need something to prevent that from happening. Because what is the main purpose of the charger? People often forget this. A lot of people think, oh, it's to keep your load circuits energized and make sure that the switchgear doesn't shut down. No, actually, the main purpose of a charger is to charge your batteries. Okay? That is really its only purpose, is to keep your batteries charged. So if you lose power, your DC circuits will remain powered from the battery. And the thing about batteries is they are very sensitive to charge voltage. So a 60-cell lead acid battery needs to be charged at approximately 135 volts DC, which is 60 cells times 2.25 volts per cell at 77 degrees Fahrenheit. This is basically an approximate assumption. You have to look at your battery data sheet to make sure that the float voltage is what you think it should be. Some manufacturers like to see 2.23 volts per cell. Some manufacturers like to see 2.27 volts per cell. And sometimes they are quoted at 20 degrees Celsius. You've got to be careful about all these things. You need to make sure that the appropriate charge voltage is given to your batteries, because if you overcharge them, they can go into thermal runaway, and if you undercharge them, they can lose life rapidly because the plates will suffocate. Okay. So a high voltage, it says there, will cause excess water usage in wet cells or thermal runaway in valve-regulated cells, and a low voltage will cause sulfation of the plates. Both causes a loss of life in the battery. So we need a way to control the output voltage when we cannot control the input voltage, okay? And we can't control the input voltage. That's what's coming from the electricity distribution company, okay? And to do that, we replace the diode with what's called an SCR. It's a silicon-controlled rectifier, okay? Once again, it's an interchangeable term with the term thyristor. And it means it is a diode that can be turned on, but it's extremely important, very, very important to understand that it cannot be manually turned off by removing the gate signal. And we'll go into that in a moment. So it is turned on by sending a signal to the gate of the device, okay? But it will only turn off when there is close to no current flowing through it. In other words, the holding point. And fortunately, in a sine wave, that is the zero crossing point. When there is no potential across the anode and cathode, there is nothing pushing current through the SCR, and therefore there's no current flowing through it, and it will turn off itself automatically. So here is the electrical circuit diagram for an SCR. So if we took away this gate lead here, it would be a diode. We have the anode, we have the cathode, and that's all you need. But with the SCR, we add a gate lead, and that's basically connected. It's not connected to the cathode, but we do send the signal with the gate with respect to the cathode. Okay, and all SCR manufacturers have a different voltage level that they need to turn their SCRs on, but 5 volts is typically a common value to get your SCR to turn on. But you'd have to send that signal 5 volts positive on the gate with respect to the cathode. Okay. This stud mounted one is quite easy to see. The red sleeving indicates that that is the cathode. Okay, so therefore this red lead here is also connected. It's actually connected directly in there. That is also a cathode, and I'll explain that in a moment. This white lead here, that is the gate. And then this stud here, that is the anode. Okay. So what you would do is you would have your circuit that turns the SCRs on. You would have that connected to the 2 flying leads that come out here, the gate and the cathode, and you would send your 5 volt signal or whatever it is along there. But the main power connections would be connected to that point there and to that point there. This is a hockey puck version, just like the hockey puck diode. They have to be sandwiched between 2 heat sinks, and you can see we have the gate cathode leads coming off there. This stud mounted one only has a gate lead, so therefore you would have to make your own connection to the cathode to get the gate cathode connection, and obviously that's still the anode. They're quite rare. You usually always have a red cathode lead coming off. And then this is a multi-pack. So you can see the symbols here. You can see there's 2 SCRs in here, and we can say that's the anode and that's the cathode. And let's have a look. That's the anode, and if we follow it over, that's the cathode for this one. And these are the gate drive circuits. I can't tell from here, so let's say that one's the gate and that one there is the cathode. Okay. The interesting thing about the modules like this is they're completely isolated from the base. There is a metallic base on this, so it can be attached to a heatsink, but that is only for heat transfer and heat transfer only. Okay, because these devices do get hot when there's current flowing through them, so they have to be connected to a heatsink so that that heat can be dissipated. But these, none of these connections here are connected to the actual base, the physical base of the SCR package there. So you can actually put, if you had basically a heatsink there, you could put another package of SCRs there, and there's going to be no interaction between this base plate and the terminals. You can put as many SCR packages like that on one heatsink as you want, as long as the heatsink is rated to take away the heat that's generated. Okay, so the difference between an SCR and a diode is the gate lead. Okay, and I'm going to try and show you the mechanical equivalent. So yes, it is like a check valve, okay, but what we've done is we've added this gate, okay? So it's exactly the same as a diode, but we've added a gate. So if the gate is closed, in other words, there's no gate signal, oil cannot flow anode to cathode, and it cannot flow cathode to anode. It will be an open circuit in both directions. It's as if it's just an open. That blocks any current from flowing when there isn't a gate signal. But when we do send a gate signal, the gate lifts up and it allows oil to flow this way here from the anode to the cathode. But remember, it's still a check valve. If we try to push oil that way, the clapper will close and it will prevent oil flowing through that way there. So the gate just allows the device to act like a diode. It doesn't allow it to conduct in both directions. Now, the complicated thing when you try and think about it as a mechanical device is, okay, how does it, when I mentioned that you can switch it on, but it doesn't switch off, well, the best way mechanically I can think about it is the gate is actually attached to a mechanism. Now, remember, this is just imaginary, just to give you an idea of mechanically how it would work. So if we have flow of oil going this way here and we have lifted the gate up, the flow of oil is pushing against the gate there and it's pushing it onto that ledge, and the spring is there. Once the oil stops flowing, the spring will push that back out and allow the gate to shut. But as long as current is flowing in this direction, once you turn the gate on, it will stay on, and it will stay on forever. Okay, as long as there is positive there with respect to negative there, and current flows. Okay, but as soon as current, as soon as current stops flowing, that spring pushes it back and allows the gate to close, and the gate stays closed until we receive another signal to turn the gate on, and then it will lift up, current will flow, and it will push back onto that ledge again. Obviously, that's not how an SCR works. It's just an analogy of how it works. Okay. So what is the most basic purpose of a valve? Another very good question. Why do we use valves in the first place? And you can see the picture there of a faucet. It's to control the flow of liquids. Usually that's why we use a valve. You can either have it off or you can have it on, or you can have it somewhere in between. It can regulate the amount of fluid flowing through a pipe. That is the purpose of a valve, and that is the exact same purpose for an SCR. So we have this circuit here, very, very simple circuit. Okay, we have our AC single phase input coming in here. We have our lamp here, okay, and then we have our SCR here. So hopefully you can see if we send a gate drive to the SCR, okay, then it will turn the SCR on and will allow current to flow through the lamp, and the lamp will light. Okay, so you can see here this little pink purple. This is the gate signal that's getting sent to the SCR. And then this waveform is what happens when we send the gate signal to the SCR right at the start of the sine wave. Okay? And when we do that, we allow the full sine wave to get through, and then it gets to the zero crossing point and it turns itself off, because what happens is we change direction and we try and force current the other way, and current can't flow that way, so the SCR blocks current because it's gone past the zero crossing point and turned itself off. And that repeats right here again. We're turning the gate signal on right at the start of the wave, and we allow the full sine wave to get through. So when we turn the SCR on right at the start of the sine wave, the lamp will be at its brightest. Okay? And conversely, this bottom one here, we're sending the gate signal, at this point here, and we're only allowing a very small portion of the sine wave through. Once again, we cannot control it turning off. The zero crossing point turns the SCR off, okay? And you can see that we're sending a lot less power out to the output now, so the lamp won't be as bright. And this is basically how a rudimentary dimmer switch would work on lighting. You just have a potentiometer, the knob that you turn to turn the brightness of the lights up and down is a potentiometer, and that controls the gate signal going to the SCR, and basically turns the SCR on later in the cycle or earlier in the cycle to make the lamp brighter or dimmer. Now, it's important to remember here, we're sending a pulse on this top waveform here. So at this point here, we're not sending a gate signal until this next gate signal here. But look, it still stays on, because remember, we cannot turn that SCR off. Once it's on, the only thing that turns it off is that zero crossing point. Very, very important fact to remember. Okay. And this is a 6-pulse fully controlled rectifier. So this is for a 3-phase system. Okay. And it's exactly the same as a diode bridge, but here it's drawn that we have the gate cathode leads here. But it still operates exactly the same. It just means now we can control when these diodes, well, SCRs, turn on. Okay. And this waveform, once again, on the 3-phase system, here's where the gate trigger signals come in. And then basically here's the waveform. And then the next one, the yellow one, starts here. And then that gets turned on at that point there. And that point gets rectified to this position here. And then the blue one turns on. And that gets turned on at that point there. So this would be the DC output from a 3-phase controlled bridge. And that's being turned on at the halfway point in the sine wave. Okay. So the next question that many people ask is, what about the gaps? Once again, we have a simple rectifier here. We've got AC going in on the left-hand side. This is drawn a little bit different. Now we're using a center-tapped rectifier, which is used on some small control power systems. But let's do the current again. If it's positive to negative there, then it will flow out through that way, down through the resistor, and out back into that way there. And if it's positive with respect to negative, it's going to go out that way there, up there, and back. So it's exactly the same as the other bridge that we drew. We're just using 2 devices and a center tap transformer. The main point that I'm trying to get over is we still have the same waveform here, and we do have these gaps. Okay, we don't want these gaps here. What we want is lovely, smooth DC to be able to charge a battery, because during these portions here, if you're charging a battery, that battery is discharging. So it's charging at this point here, and then it's discharging when we go down into the troughs. The peak charge and the troughs discharge. And that's not good for batteries. So what we do is we add an inductor capacitor, an LC circuit. And if you basically put this rectified waveform into this LC circuit, then the output becomes this. Now, it's not perfect, but it's much more like the DC that a battery requires. And the bigger the capacitors and inductor, the smoother the DC will be. And filters are used to reduce the amount of AC content being seen by the battery. High AC ripple is bad for batteries. The filter consists of an inductance and a capacitance. The inductor is in series with the battery and the capacitor is in parallel. And the inductor is usually placed before the capacitor. And capacitors are like short-term batteries, and the electrolyte inside them does degrade over time and temperature. Most capacitor manufacturers recommend that the DC electrolytic capacitors are replaced every 10 years. If the ambient temperature is hotter, then that time period is reduced, and quite drastically as well. So try and make sure that your capacitors are kept, that the room that your equipment is in is air conditioned to prolong the period of time, the lifespan of those capacitors. DC electrolytic capacitors are polarity conscious and must never be connected reverse polarity. That's how you let the magic smoke out. And when they fail, they can explode or catch fire. And a degraded DC capacitor can cause higher AC ripple to be seen by the battery. An inductor is just a coil of wire around an iron core. Basically, if you think of the primary of a transformer, so you have your primary here, and that's the core, that part there, then that really makes up an inductor. It's just a coil of wire wrapped around a core, and they very rarely fail. But the coil opposes changes in current by storing electrical energy. And as the current increases, so when the current increases, it stores the energy in the core, and then it releases that electrical energy if the current decreases. So basically, the voltage going up and down tries to keep the current steady. That's what an inductor tries to do. A capacitor tries to keep the voltage steady, and an inductor tries to keep the current steady. And both together, they do a very good job. So how do we control the output voltage? And the answer to that is by using feedback. We have a feedback circuit that is connected to the SCRs that can control the output of the system. And here's the basic feedback circuit. And I like to look at it as the most common thing that we can use every day. And that would be cruise control in your car. Okay, so in every system you have a reference, a controller, the system that controls everything, and a sensor. Okay, that's the main components of a feedback circuit. Okay, so for cruise control, you have your set point, your desired speed. So that's when you press your button on your steering wheel or wherever it is and say, okay, I want to go 70 miles an hour. Okay, so the controller tells the throttle unit, I want to go 70 miles per hour. And then therefore it tells the engine and gearbox to speed up or to 70 miles an hour. And then we have a speed sensor on the wheels. And once we get up to 70 miles an hour and these two inputs match, it says, okay, we are now at equilibrium. The controller says, okay, we are now where we need to be. We don't need any more throttle or anything changing in the engine. Okay. And then obviously this is happening many times a second. So if it did take the foot off the gas, the wheels would slow down, and therefore there would be an error between this point and this point, and it would say, okay, I need more gas. So it's constantly doing that for you. That's what cruise control is doing. And if you went, let's do it like this. So you're going 70 miles an hour and then you get to a hill. Okay, well, the speed sensor is going to say, wait a minute, we're going up a hill. That means our wheels are slowing down. I need to increase our speed. So it tells the throttle unit to put more gas out. It says to the engine and gearbox, right, we need to go faster until the wheels get to 70 miles per hour again. And we're all good. And then when you go down the hill, the speed sensor says, okay, we're going too fast. So the feedback circuit says, okay, we need to take our foot off the throttle and not go as fast until we get back to 70 miles an hour. That's the basics of a cruise control. And that's exactly the same as a charger feedback circuit. Instead of pressing the button on your steering wheel, we set the float equalize voltage levels. And then that measured value goes into the control board. And then the control board sends signals to the SCRs on when to turn on. We're not going to talk about the current sensing just now. We're just going to talk about the voltage sensing. Okay, so if we want 135 volts DC to charge our batteries, which is exactly the same as setting 70 miles per hour, the feedback circuit says, okay, I'm going to turn the SCR bridge on enough until this output circuit, the voltage sense circuit here, says, okay, I am now at 135. So that's its equilibrium. That says everything is okay. But then remember, if our AC input into the system goes down, then our DC voltage is going to go down. So our voltage sense circuit is going to say, oh, wait a minute, something, I don't know what it is, but something is causing my voltage to go down, let's say to 130 volts. So it sends that error signal here. The control board says, okay, I need to turn my SCRs on earlier in their phase cycle and get more voltage to the output. And then the sensing circuit will say, okay, keep on doing that until I get to 135 volts. And when it does, it goes back to its equilibrium again. And once again, this feedback circuit is constantly sensing the output of the system all the time. And it's constantly adjusting as necessary to whatever the float voltage has been set to, or the equalized voltage has been set to. And here's just a drawing of one of our chargers so you can actually see it in action. So we have our 480 volts coming in here through the primary of our transformer. And you can see there's absolutely no electrical connection between the primary and the secondary. And then our secondary, that is where our 130 volts windings are. And then they go through 3 fuses, A phase, B phase, and C phase fuses, and then into our SCR bridge. Okay, we have 6 SCRs here. And you can see the gate leads go up to our control board. Okay. And the control board is what sends the signals to the SCRs. And then we can see that this is our voltage feedback. It's measuring the output voltage and making, basically that's the tachometer on the wheel of the car. That's measuring our speed, or our voltage in this case. And then we also have what's called a current shunt that is monitoring the current. But we're not going to go into current control in this webinar. And we're nearly out of time, so I need to go as fast as I can. So remember, if our input goes down, the DC goes down momentarily, okay? And the SCRs have to be gated earlier to increase the average voltage until this point goes back to 135 volts. And then if the AC goes high, the output goes high momentarily until the feedback circuit takes over and the SCRs are gated later in their cycle, which will decrease the average voltage. Whew. Okay. Oh, bang on time, 11 o'clock. So now it's time to go over the the questions that have come in. So let's have a look what we have here. From your operating experience, have you ever found a failed gate input on an SCR? SCRs are extremely reliable devices. They've been around for 80, 90 years, and they are just so robust. But there are manufacturing defects that happen, but it is very, very rare. So have I ever found a failed gate input? Yes, I have found a gate input failed on an SCR. It's usually on the modular type SCRs. They have those fast on connectors that you pushed a crimp connector onto. Sometimes that very thin piece of metal gets damaged when you're putting the cable on, or in manufacturing it got damaged, and the actual gate connector is not connected to the gate inside the SCR itself, so it can fail that way. So it's usually always a physical problem between the gate cathode connector. But yes, it can happen, but it is rare. Somebody's asked, are there any considerations on the K ratings? I don't quite understand that question. So Abbas, if you can clarify what you mean. I don't know what the K ratings are. Somebody's asked, if I replace an SCR for high current, it needs copper grease. Yes. If it is mounted to a heatsink and it is a stud mounted SCR, yes. And this can be very, very confusing because let me go back. Unfortunately, Webinar Jam doesn't allow me to pick the slide I'm going to go back to. So bear with me while we go through this, because this is a very important point. Thank you for asking that question. We should be there in a moment. Here we go. So for this surface here, okay, you would have to add copper grease. Copper grease is a thermal compound that has copper in it. So not only is it good at transferring heat, it also transfers electrical current. So it is not an insulating compound. It is actually electrically conductive. And once again, on these surfaces here on the hockey puck SCR, yes, this must have copper grease on it because it gives a uniform connection between the device and the heatsink. Once again, on this portion here, you need to use copper grease. On this one here, on the base, you would use silicon compound, the white silicon compound, and that is for heat transfer only. Silicon compound is not electrically conductive. So if you put silicon compound on here and then try to run this, what's going to happen is eventually it's not going to be conductive. So the SCR is going to struggle to conduct between the base of its SCR here and the heatsink. Eventually it will find gaps to go through, but when it does that, that gives a very, very limited surface area for the current to flow through. And you tend to find if somebody has replaced an SCR that's mounted on a heatsink that should have copper grease and they actually put thermal compound on it, you will see that they fail very, very quickly because the surface area that is actually conducting is very, very small indeed. So very good question. Put copper grease, which is electrically conductive, on these, but do not put silicon grease on these. You can put silicon grease on this package. In truth, you can put copper grease on this one as well if you wanted to. It would be a waste and messy because there's no electrical connection between the base there. So just use normal silicon compound for this one, but please do use copper grease for this one. It's a very common mistake. How to calculate value of the capacitor and the inductor? Another good question, and that is out of my skill set. That is what our design engineers do. I went through engineering school. I did my calculus stuff 30 years ago, and that's where they stay. I don't use calculus anymore. There is calculations on how to do it. You can search Google, but it is out with my skill set. I do apologize, but you can find that information on Google. Is a hysteresis set for the feedback loop? Yes, most manufacturers will have some form of hysteresis set, and hysteresis is just basically a band where we don't keep on going all over the place, tracking the error signal. We put a little bit of sponginess in there, is what I call it, where the output doesn't go up and down, constantly trying to follow the variation. So there is a little bit of what you could call hysteresis put into our feedback circuit. Could you briefly talk about harmonics seen by the supply system? Once again, it's a little bit out of my knowledge base, as in knowing the third, the fifth, the seventh, and how much is reflected back. What I will say is, for a rectifier bridge, let's start off with a single phase, fully controlled bridge. That is going to reflect a huge amount of harmonics back onto the supply system, because it's only switching basically twice every 60 hertz, and that switching will be reflected back onto the supply system. For a three-phase system with 6 SCRs, it's not as bad, but the harmonics are still enough there that you have to think about the design of your charger and whether it is suitable to connect to your supply system. If you have concerns about your supply system being affected by the harmonics reflected by your charger, then we would always recommend that you go for a 12-pulse charger, which is basically a charger that has 2 6-pulse bridges, 6 SCR bridges in there, 12 SCRs in total, that are offset by 30 degrees. Basically, we put one set of SCRs is connected to a delta transformer, and one set of SCRs is connected to a Y transformer, and they're offset by 30 degrees, and that really does lessen the amount of THD seen by the supply system. So if you are concerned, go for a 12-pulse charger. We are in the process of designing and building a what we call our high frequency charger, which is basically, it's a power factor corrected charger. It's a charger that has IGBTs on the bridge instead of SCRs. That will nearly make the harmonics reflected back unity, the power factor unity. But in our experience, IGBTs are just way more sensitive than SCRs. You know, we're going to build it and it's going to be a fantastic system, but it's just not going to be as reliable as an SCR charger. SCR chargers run for years and years. We've got systems that are still out there that are 40 years old, and they are still running without any issues whatsoever. So yes, an SCR charger does put more harmonics back onto your supply system, but it is much more reliable. Hopefully, Tom, that answered your question. Somebody's asking about DC current limit. I really didn't want to go into current limit on this presentation because it's an old, maybe I'm going to do another presentation on that. But basically, current limit is a way to regulate the output of the charger, but rather than doing it with the voltage feedback, it's done with current feedback. If you notice, I mentioned in the feedback that we had a current shunt. get there. We're just about there. Here we go. So here, okay, we have a current sense circuit, okay, and the current sense circuit actually overrides the voltage sense circuit. So let's say that the SCR bridge could do 100 amps. In other words, the SCRs that we installed in the bridge are designed for a maximum capacity of 100 amps. So if we go above 100 amps flowing through those SCRs could be damaged. So obviously we don't want to go above 100 amps. And remember, this is just a for ease for you to see. We actually overrate our SCRs. For 100 amps. We would put 200 amp charges in our SCRs in our bridge. But this is just an example. Okay, so we're saying 100 amps is all that we can put out of this bridge. Then what we do is we actually have a current shunt on the output of the system that measures the current, and that reports back to this current sense circuit here. So if we go above 100 amps, then the current circuit says, okay, we've got too much current, and it puts an output to the error signal and says, okay, we need to tell the control board to phase back the SCRs. In other words, turn the SCRs on later in the cycle. In other words, reduce the output voltage, because the only way we can reduce current is to reduce the voltage of the charger. That is the only thing we have control over. So we will keep reducing the system output voltage until we see 100 amps going out through the current sense circuit. That could mean that the voltage goes down to 110 volts. If necessary, it could even go down to 0, I suppose, in theory, but there are many other things that would shut the charger down in that case. But even though it is called current limit and we are limiting the current, we are doing it by controlling the output voltage. Okay, so hopefully that explains a little bit about current limit. And I will try and do another webinar that goes into current limit a bit further in depth. Austin, great question. What is an acceptable AC ripple current to a 60-cell lead acid battery? Unfortunately, it is manufacturer specific and size specific. It would be great if I could give you an amount. Some manufacturers say it's 3% of, actually, is it 5% of the C10 rating of the battery? But once again, it is specific to the battery and the size of the battery. And I do have a webinar that discusses that. So go to our YouTube site. I can't remember which one it is, but it's either in the battery webinar or in one of my other charger webinars. But if you go there, it explains quite a lot about AC ripple, how it is affected by the charger. So good question. I just can't answer it. I just don't have time. And we do have a webinar that covers it. Somebody saying capacitors should be replaced every 5 years. No, capacitors in AMETEK SCI chargers should be replaced every 10 years. We put in special capacitors made by our partner who makes capacitors, and they are rated for 10 years at the operating temperatures designed for our systems. If you go out with those temperatures, then they will reduce, but we recommend our capacitors are replaced every 10 years. Some other manufacturers use cheaper capacitor manufacturers, and they have a shorter lifespan, and it may well be that they need to be replaced every 5 years. But for AMETEK solid-state controls, our systems are robust industrial systems, and they will last 10 years. Are DC capacitors on charger output considered an option or mandatory? Great question again. In this day and age, they should be mandatory. And when we sell our chargers, I'm pretty sure they are mandatory now. In the olden days, when people didn't know about ripple and ripple current and what it did to batteries, it wasn't mandatory, and that was a problem. In truth, a battery, because of its plates, does have some capacitance. So it does act as a filter itself, but in doing that, it charges and discharges the battery. So if you are going to buy a charger, always make sure there are DC capacitors on the output. Okay, we have noticed charger voltage drift. What may be causing it? That's very, very difficult to tell. That could be a control board issue. It could be that your AC input is fluctuating. There could be a loose connection. Unfortunately, this webinar is not long enough to be able to figure out what you've got going on there. I do apologize, but it could be many, many things. Okay, I'm going to put it out there. If anybody has any other questions, while I wait for those, I will say, as always, that this webinar was recorded. It will be put on our YouTube site tomorrow. Our marketing team is fantastic. They're going to put a link into the chat so you know where to go and view that YouTube video. And also, if you have any issues, problems, questions, concerns, whether it comes about the servicing or purchasing a new UPS, you can contact us using the website or the phone number that is on our website. The marketing team is going to put that into the chat as well, so you know how to contact us. All of the emails that you send to Solid State Control Service do come to me. I get to see them all. So if you have any questions, use that email address, SCI marketing@ametek.com, and they will send it on to me. Any questions, don't hesitate to reach out. So sorry, I've gone 17 minutes over. I do know that your time is precious. I do try and stay as close to an hour as I can, but unfortunately, I really enjoyed speaking about this kind of stuff. So hopefully I've answered all of your questions and that the training today was enjoyable for you and you learned something new. That would be a good thing. I don't see any other questions coming in, so I'm going to sign off, say thank you very much for joining us. Watch your emails for the next webinar. It's going to be in about 4 weeks' time. If you have any suggestions on what that webinar should be, please fill out the survey that is going to be sent out. I think it's question 5 asks what you would like the webinar to be about. Please let me know. I read every single one of those surveys because I want to know what you want me to discuss at the next webinar rather than go over stuff that I've gone over already. So take care, enjoy the rest of your day, and thank you for joining us on this wonderful Wednesday, the 22nd of June. And take care until next time. Thanks very much, everyone. Bye-bye.